Identify the asymptotes and graph this rational equation right here. All right, well, first things first, there's going to be two asymptotes that we're going to look for. The vertical asymptote, okay, the vertical asymptote, so much writing, is going to be whatever number makes the denominator equal to 0 and therefore makes this undefined. -1 is going to make the bottom here equal to 0, because if I were to do x plus 1 equals 0, subtract 1 from both sides, I would get -1. So x equals -1 is going to be my vertical asymptote. My horizontal asymptote, more writing. Use this time to like and subscribe and make a comment, your favorite type of asymptote. Anyway, horizontal asymptote is this number right here. Okay, the number floating around on the outside that does a vertical shift up or down. Since this is -2, my horizontal asymptote is the equation y equals -2. Now, in order for me to graph, I'm going to look for two more things, okay? I'm going to look for the x-intercept, and I'm going to look for the y-intercept, okay? So let's do the x-intercept first, okay, the harder one. The x-intercept, also known as the 0, also known as the roots, is what happens when you set f of x equal to 0, okay, because your y is going to be equal to 0. So if we do that, we would have 0 equals 3 over x plus 1 minus 2. If we add 2 to both sides, that gets me 2 equals 3 over x plus 1. Multiply both sides by x plus 1. All right, so we're going to have a little bit of distributive action over here. X plus 1. So 2 times x is 2x. 2 times 1 is 2. So we have 2x plus 2 equals 3, because that cancels out. Okay, since I'm running out of space, subtract 2. 2x is going to equal 1. And then divide by 2, and we have an x-intercept happening at 1/2. Okay, so that's going to be my x-intercept. That's going to happen at 1/2. Now to find my y-intercept, which is a whole lot friendlier, you are going to set, we'll say y equals instead of f of x equals. You're going to set 0 equal to 1. So you're going to get y equals 3 over 0 plus 1. I'm sorry, x equals a 0, minus 2. So I have 3 over 1 minus 2, which is 3 minus 2, which is 1. So that's going to be my y-intercept. So let's graph all of these things that I found out, and from there I can sketch, for the most part, what this picture is going to look like. My vertical asymptote is a vertical line that goes through -1, so it's going to look like this. No part of my graph is going to touch that red dashed line. My horizontal asymptote happens at x equals -2. Now, rational functions look one of two ways, either like this, right, or like this. These numbers are going to help me which version I'm going to get. My x-intercept is going to be 1/2, so I'm going to put a dot right there. Okay, my y-intercept is going to be 1, so I'm going to put a dot right there. What this tells me is that in order for me to draw this out, I have to have a line that goes through these two dots, which means I have this version right here. So we're sketching now. We're not looking for perfection. But we're going to draw a curve that goes through these dots and kind of levels out at the asymptotes, like that. Okay? Obviously, no perfection. If I wanted to pick points and plug them in, I guess I could do that. But I'm just going to kind of sketch it out nicely and have my green line follow the asymptotes. Okay? So that's how you graph a rational function along with identifying its asymptotes. Fun stuff. Identify the asymptotes and graph. We're looking for two types of asymptotes. We're looking for vertical asymptotes and we're looking for horizontal asymptotes. Okay? Now, the vertical asymptote is going to happen at the number that makes my denominator here equal to 0. Now, if I were to plug in -1 for x, negative 1 would make the bottom here equal to 0 because I would get 4 over negative 1, and that's undefined. So my vertical asymptote is x equals negative 1. The horizontal asymptote exists at the number that's being added to the whole thing because that tells me the shift up or down. Whenever I have like a nice looking rational function like this, okay, it's supposed to level out at the zeros at the x-axis. But by adding 1 on the outside, that shifts everything up 1. So y equals 1 is going to be my horizontal asymptote. Now, if I want to graph, I have to remind myself that rational functions are going to look one of two ways. It's either going to look like that, or it's going to look like that. Oh boy, I'm going to screw that up. There we go, much better. Ignore that little line right there. And maybe by erasing it, it'll help me ignore that little line. Look at that, magic. All right, so I'm thinking, all right, well, how can I figure out which one is which, and how can I be a little bit more specific with my graph? Well, let's find ourselves our x-intercept, which is kind of frustrating to do, but that's all right, and our y-intercept. By doing that, we'll be able to put 2 points on the graph and figure out which one of these guys we're dealing with. In order to find the x-intercept, you're going to substitute f of x with 0 and solve. So not the prettiest looking thing in the world at all, but that's okay. If I subtract 1 from both sides, I'm going to have negative 1 equals negative 4 over x plus 1. If I multiply both sides by x plus 1, I got a little bit of distributive property action going on here. You cross out, I have negative x minus 1 equals negative 4. Let's add 1 to both sides. I'm not really showing my work here because I don't have the space, so add 1 to both sides gets me negative 3. And if negative x is negative 3, then positive x is positive 3. So that's my x-intercept. My x-intercept is going to happen at x equals positive 3. Okay, not so bad. Not good either, but not so bad. My y-intercept is a whole lot more pleasant to figure out. Let's substitute f of x with y because it just looks prettier. In order to find my y-intercept, you're going to replace x with 0, so negative 4 over 0 plus 1 plus 1. So that becomes negative 4 over 1, which is just negative 4 plus 1. And y is going to equal negative 3. So that's going to be my y-intercept. So I have 2 points here. I have x equals 3, so u happen. And I have y equals negative 3, so u happen. Also, I have a vertical asymptote living at x equals negative 1. Okay, let me use a little nicer line. There we go. So, okay, nice vertical line going through negative 1. I have a horizontal asymptote at y equals positive 1. So you go through here. And now I have a good idea of which function I'm going to deal with. Okay, since my line, my curve has to go through these 2 points, it's going to look like this option right here. So not looking for perfection, just looking for accuracy. I'm going to use my asymptotes as a guide because things start to level out at my asymptotes. Okay, and I'm going to use my asymptotes as a guide right there. And then I'm just going to try to draw something very similar over here. Okay, you could use points to plug in. That's okay. Here I'm not looking for perfection. I'm looking for accuracy, right? And so this is going to be the graph of the rational function. So pretty crazy stuff. Identify the zeros, holes, and vertical asymptotes. If I'm given a rational function, okay, in order to find zeros, holes, and vertical asymptotes, I'm looking at factors. If it helps, pretend that these are parentheses. If it helps, you don't need to. Zeros exist when you have a unique factor living in the numerator. That's where a 0 is going to live. A vertical asymptote is going to live if you have a unique factor living in the denominator. A hole is going to exist if you have factors up in the numerator that's exact the same amount as the factors you have in the denominator. So if I have just one random thing living upstairs, that's a 0. If I have one random thing living downstairs, that's a vertical asymptote. And if I have the same thing living upstairs and downstairs, that's a hole. Now let's take a look at what I have. X minus 2 is nothing like x minus 4. Since you're living in the numerator, you are a 0. And in this case, my 0 is the opposite or the number that makes this positive. So my 0 makes this 0, I'm sorry. So my 0 is going to be x equals 2. Since I have a factor that's nothing like a factor up here, x minus 4 in the denominator, that's going to be a vertical asymptote. And whatever number makes that 0, which is going to be 4, is going to be my vertical asymptote. So my 0 in this case is x equals 2, and my vertical asymptote in this case is x equals 4. Do I have any holes? Nope. And that's how you do it. Identify the zeros, holes, and vertical asymptotes. Well, if you're given a rational function, you're probably going to have to factor stuff out. A 0 exists when you have a unique factor in the numerator that's nothing like the denominator. A vertical asymptote exists if you have a unique factor in the denominator that's nothing like the numerator. And a hole exists if you have the same thing in the numerator that you have in the denominator. So what we need to do is we need to factor all this out. So the first thing I can do here is I can factor out an x, which leaves me with x squared minus x minus 6. And as you can take a look at that, we're not done. I can factor a negative 3 out from the bottom here, the denominator. That leaves me with x squared plus x, oh, didn't mean to do that, x squared plus x minus 6. The x still lives out here. Factoring this further, two numbers that add up to negative 1 and multiply out to negative 6 are going to be x minus 3 and x plus 2. Now don't get your hopes up. Okay, the number down here, negative 3 is still there. The numbers that add up to positive 1 and multiply out to negative 6 are going to be x plus 3 and x minus 2. I have 5 x's floating around. Let's figure out what each important number is before I start labeling these things, okay? We need to figure out what number is going to make each x factor equal to 0, okay? Well, if x is all alone, x equals 0 will make that 0. X minus 3 says if I were to make x equal to 3, I get 0 there, so 3 is the magic number. Negative 2 would make this factor equal to 0, so x equals negative 2 is the magic number. Negative 3 down here would make u equal to 0, so negative 3 is the magic number. 2 is the magic number down here because that makes u 0. Now let's go through each of these and label which is which. Again, if you're looking upstairs and it's unique, that's going to be a 0. If you're looking downstairs and it's unique, that's going to be vertical asymptotes, and anything up or downstairs that's the same is going to be a hole. X equals 0 is nothing like everything else. You're a 0. X equals positive 3 does not repeat. Close, but not the same, so you are also a 0. Similarly, x equals negative 2 does not repeat down here, so you're a 0. On the bottom, I don't care about negative 3. There's no x. Ignore it. X equals negative 3 here, though, does not repeat upstairs. You're a vertical asymptote. X equals 2 in the denominator doesn't repeat up here. You're also a vertical asymptote. So I have 3 zeros, okay, and those are x equals 0, 3, and negative 2. I have 2 vertical asymptotes, and those are the equations x equals negative 3 and x equals 2. I have no holes. So this right here is going to be my answer. Identify the zeros, holes, and vertical asymptotes of this rational function right here. Well, what we need to do is we need to factor this guy out. And once we factor this guy out, this is what we look for. Any unique factor that lives in the numerator is going to be a 0. Any unique factor that lives in the denominator is going to be a vertical asymptote. Any factor that is the same in the numerator as the denominator is going to be a hole. So I need to factor this guy out and see what I have to work with here. So factoring out the top is going to be 2 numbers that add up to 1 and multiply out to negative 6, x plus 3, and x minus 2. What I can do here is I can pull out a negative 4, so let's factor out a negative 4. That leaves me with x squared plus 4x plus 3. Now I can keep factoring in the denominator there. Okay, that negative 4 doesn't matter. Two numbers that add up to 4 and also multiply out to 3 are going to be x plus 3 and x plus 1. Now I have 4 x factors, 2 in the numerator, 2 in the denominator. That negative 4 is not going to help me at all in answering this question because there's no x attached to that negative 4. But let's figure out the magic numbers, the numbers that make each factor equal to 0. If I have x plus 3, then negative 3 is going to make that factor equal to 0. If I have x minus 2, then positive 2 is going to make that factor equal to 0. If I have negative 3, then x equals negative 3 is going to make that factor equal to 0. And if I have positive 1, then x equals negative 1 is going to make that factor equal 0. Now I take a look at each of my 4 x values and I figure out whole, zero, or vertical asymptote. I have x equals negative 3 in the numerator, which happens to repeat in the denominator, which means you are a whole. I have x equals 2 in the numerator. That doesn't repeat anywhere else, especially in the denominator, so x equals 2 is a 0. I have x equals negative 1, which is all alone in the denominator. That's a vertical asymptote. So my whole is going to be x equals negative 3. My 0 is going to be x equals 2. And my vertical asymptote is going to be x equals negative 1. Very important stuff if you're going to do AP Pre-Calculus. Make sure you know it. Identify the zeros, wholes, asymptotes, and sketch. All right, so I'm looking for zeros, wholes, and asymptotes, and what I'm going to do is I'm going to factor out as much as I can to help me find zeros, wholes, and asymptotes. Why? Well, first things first, a 0 exists if I have a unique factor in the numerator. A vertical asymptote exists when I have a unique factor in the denominator. A whole exists if I have repeating factors in the numerator and the denominator. All right, so let's factor stuff out. Okay, let's factor stuff out. Really, the only thing I can do as far as factoring things out is rip out a negative 2 on the bottom. So I have a factor of x plus 4 up here. If I pull out negative 2 down here, that leaves me with x plus 3. So my magic numbers are going to be negative 4 because that's going to be the number that makes the numerator's factor equal to 0, and negative 3 for the same exact reasons. Negative 4 is a unique factor in the numerator which makes it a 0. So I have a 0 at x equals negative 4. Now negative 3 is all alone in the denominator, which means I have a vertical asymptote at x equals negative 3. What I don't have is I don't have a whole to deal with. Great. Now, one of the things that I didn't do is I didn't do a horizontal asymptote. Whenever you're not adding or subtracting a number on the outside, the way you figure out the horizontal asymptote is if you notice the degrees in the numerator are the same as the degrees in the denominator, your horizontal asymptote is going to be the ratio of the leading coefficients. Since I have a degree of 1 up here and an invisible 1 in front of that leading x and a negative 2 down here, my horizontal asymptote is going to be y equals 1 over negative 2 or negative 1/2. Okay, now one thing that I'm also going to do in order to figure out what my x-intercept is, because that'll help me, or my y-intercept is, because that'll help me graph things. My y-intercept is going to be whenever x values are equal to 0. So I'm going to add one more point here to help me graph this. Okay, my y-intercept is going to exist when my x values are equal to 0. So I'm going to pretend these aren't here. 4 over negative 6 simplifies to negative 2/3. So now that I have this information, I can sketch out some kind of important numbers. This is a sketch. This isn't 100% accurate. This is just a sketch. I have a 0 at negative 4, so negative 1, 2, 3, 4, so let's go out a few more. My graph is going to go through there, okay? I have a vertical asymptote at negative 3. okay, I have a y-intercept at negative 2/3. So let me, so negative 2/3 would be like somewhere around here. And I have a horizontal asymptote just above it at negative 1/2. Now I know rational functions are going to look one of two ways, like this or like this. Now the only way that this will work out is if I choose this version right here, because what's going to happen is you're going to kind of hover nicely along here, go through there, and start leveling out there, and you're going to go nicely through here and start leveling out there. Is it the perfect, prettiest graph in the world? Absolutely not. But is it accurate enough for me to make a sketch and know that it's going to kind of look like one of these and kind of go through that and kind of go through that? Yeah, and I'm happy with it. Simplify and state domain restrictions. All right, so what I have is I have a p plus 4 living in the numerator and something that looks factorable in the denominator. So let's factor that out. P plus 4 numerator. Denominator is going to be two numbers that add up to 6 and multiply out to 8. So how about p plus 4 and p plus 2? Okay, now my domain restrictions are going to be any number that makes a denominator's factor equal to 0 before I even think about canceling stuff out. Okay, p equals negative 4 is going to make this factor equal 0. P equals negative 2 is going to make that factor equal to 0. So what's going to happen is no matter what, my domain restrictions, my DR, is the fact that P cannot equal negative 4 and it cannot equal negative 2. Now what I can do after I state my domain restrictions is cross out any factors that's the same in the numerator as it is in the denominator. Once I do that, I'm left with just 1 up in the numerator and p plus 2 in the denominator. So even though I got rid of the factor p plus 4, it is still a domain restriction because you cannot plug in negative 4 into the initial problem without making the bottom equal to 0. So domain restrictions are done before you simplify. Very important to do that. Simplify and state any domain restrictions. Well, it looks like in the numerator I can factor stuff out, and same thing with the denominator, so let's do that. So two numbers that add up to invisible 1 and multiply out to negative 6 are going to be x, plus 3, x minus 2. In the denominator, you have x, two numbers that add up to 8, multiply out to 15. How about 5 and 3? So let's write it out in this order, x plus 3, x plus 5. Now, simplify means try to get rid of stuff. But before you even consider that, we have to state our domain restrictions. Our domain restrictions are going to be any x value that makes a factor in the denominator equal to 0. I don't care about the numerator. So x equals 3 is negative 3 is going to make that factor equal 0. X equals negative 5 is going to make that factor equal to 0. So my domain restrictions are done before I simplify because I am not allowed to plug in either of those numbers into the original equation, even knowing very well that one of these guys is going to cancel out. So my domain restrictions are me saying x cannot equal negative 3 and negative 5. Now that I have my domain restrictions written out, I can get rid of you because you're the same. And that leaves me with x minus 2 over x plus 5. So even though I got rid of the part that has negative 3 involved, I still cannot plug in negative 3 into the original function because it makes the bottom equal to 0, and that's not allowed. Simplify and state domain restrictions. Before we state or simplify or state domain restrictions, we need to factor as much as we can, and everything's actually pretty much factored. So let me write these all out in parentheses. Now, the nice thing about multiplying is that you are going straight across the top and straight across the bottom. Now, before I start hacking away and getting rid of things, I have to state my domain restrictions. My domain restrictions are the numbers, the x values that makes a factor in the denominator equal to 0 before I start crossing things out. Okay, so x equals a -6 would make that equal to 0. X equals 8 would make that equal to 0. X equals -10 would make that equal to 0. Okay, so domain restrictions are any number that makes the denominator equal to 0 before I start hacking things away. So I will say that x cannot equal -6, 8, and -10. Now I can start getting rid of stuff. So x minus 8 up here, x minus 8 down there, get rid of them. X plus 10 up here, x plus 10 down there, get rid of them. That leaves me with just 4x in the numerator and just x plus 6 in the denominator. And that's it, I'm done. Simplify and state domain restrictions. Well, before we do anything, let's factor out as much as we can. Okay, so I have 1 here. I have 5p squared down here, not much I can do. Divided by, I can bring out a 9p minus 4. I can bring out a 5p squared. That leaves me with p minus 7. All right. Now that I have that, my domain restrictions are going to be any number that makes the denominator equal to 0. Okay, so I am not allowed to plug in 0 for this 5p squared because that'll make that equal to 0. Same thing with you. So p equals 0 is going to be a guy that makes that bottom become 0. Similarly, this factor 5p squared, if I were to set that equal to 0, I would get p equals 0 again. P equals 7 is going to be my domain restriction here because that makes that factor equal to 0. So my domain restrictions so far are going to be p equals 0 and 7. But I'm not done with this because now that this is division, I have to flip and multiply. So nothing happens with the first. But by flipping and multiplying, I have now brought that p minus 4 in the denominator, which means I now have a brand new domain restriction. I'm not allowed to use 4. So p equals 4 is now a domain restriction. Okay, and if you're like, well, do we still have to count 7? Yep, because if you plug in 7 into the original problem, it's not going to work. It's not going to work. So now that I'm multiplying, I can cross out the 5p squared, and that leaves me with just 1 up here times p minus 7, which is just p minus 7. On the bottom, I have 9 times p minus 4, so if I want to take that back and turn that back into 9p minus 36, I can certainly do that. But now I have my domain restrictions, and now you can see why I can't plug in 4, because I can't plug it into the answer. So I couldn't plug in 7 into the original problem. I can't plug 4 into the answer. This is how you do that problem. Not so bad, but not so great either. All right, time to add some pretty big looking fractions. Now, don't be afraid. Don't be scared. What we have here is we have two fractions with the same exact denominator. When you add two fractions of the same exact denominator, you just add the numerator willy-nilly. So, 5 plus 5a plus 1 is going to be 5 plus 1, which is 6. So you got 5a plus 6. In the denominator, you have a squared plus 3a plus 2. Now, normally, what you'd probably want to do is you would probably try to factor that guy out and see if there's anything to simplify. So let's just, extend the video by a minute or two so I can get that sweet YouTube money and see what happens if I do that. If I factor that out, that gives me a plus 1, a plus 2, and there's nothing I can do in the denominator to factor anything out. So in a perfect world, maybe if that was just 5a, like maybe if the problem originally had a 4 here, right? And I would be able to do 4 plus 1 to give me 5 and factor out a 5 and be left with an a plus 1. Boy, would that have been nice. But that's not what happened here. Nothing factors out. I can't do anything. So this was just a waste of time and an exercise in futility. But there you go. Simplify 3 over x plus 7 plus 4 over x minus 8. When adding fractions, you need to make sure that the denominators are the same. These guys aren't the same, not even close. Okay, and the fact that the denominators are both binomials, it's not a simple matter as maybe I don't know if I add 7. It's not that simple. What you have to do is, since they are completely different binomials, you have to multiply this fraction by x minus 8 over x minus 8, and this fraction by x plus 7 over x plus 7. Okay, by doing that, okay, I have a distributive property up here. So 3 times x is 3x. 3 times negative 8 is negative 24. On the bottom, I have x minus 8 in parentheses, x plus 7 in parentheses. Now I'm adding. We're going to do the same thing over here, all right? 4 times x is 4x. 4 times 7 is 28. And on the bottom, I have x minus 8, x plus 7 in parentheses. Now that the denominators are the same, I can add these two fractions. So 3x plus 4x is 7x. Negative 2, or 24 rather, plus 28 is plus 4. On the bottom, I have x minus 6 and x plus 7. There's nothing I can do as far as factoring up in the numerator that would allow me to eliminate any of these. In a perfect world, I would be able to factor like a greatest common factor and be left with x plus 7 and cross stuff out, but that didn't happen. Now, this is an acceptable answer, but some teachers might say, nah, you got to FOIL the bottom. So if you FOIL the bottom, you get x times x, which is x squared, right? Plus 7x minus 8x is going to be minus x, and then negative 8 times 7 is negative 56. So, although I think many teachers probably would be okay with this, this is just one step further. So there you go. Complex fractions, baby. A fraction over a fraction minus a fraction. Well, what we need to do is get this to just a fraction over a fraction. Right now, there's nothing I can do with this guy. Okay, you're stuck for now. But what I noticed is these two fractions are kind of close in denominator. If all I have to do is multiply u by 5 over 5, that leaves me with 5 over 25 minus 4 over 25. And now in this huge denominator, I can combine like terms. I can subtract these fractions. So again, 25 over 4 remains untouched for now. 5 25ths minus 4 25ths means I subtract the numerators to give me 1, and then 25ths stays that way. Now I have a fraction over a fraction. Instead of dividing a fraction, multiply the reciprocal. A fraction over the fraction means 25 over 4 times 25 over 1. Instead of dividing a fraction, multiply the reciprocal. Now, at first glance, you would look at something like this and be like, oh, hooray, the 25s are going to disappear. Oh, but that was just a mean old trick. Because once you multiply the reciprocal, you actually get 25 times 25, which is 625, all over 4. So, the answer's not horrible, but it wasn't near as pleasant as maybe you originally thought it might be. Simplify, oh my gosh, this complex fraction. Well, what I need to do first is I need to make this a single fraction over a single fraction. So what I'm going to do is I need to take this numerator up here, this numerator alone, okay, the big numerator, multiply u by m minus 4 over m minus 4, and u by m minus 3 over m minus 3. This is the only way we're going to get least common denominators, right? It's not the prettiest guy in the world, but that's what we have to do. Okay, now right now we're just focusing on everything above this huge fraction bar. We're not even touching this guy, not quite yet. We will, but not quite yet. Right now, by doing what we did, okay, we have a distributed property problem, okay? So we have 16 times m, which is 16m, 16 times negative 4, which is negative 64. Now here, this is not 4 times m minus 3. This is negative 4. That negative applies to that negative up here. So if it makes you feel better, what we could do is we can make this like, plus a negative. It does the same exact thing. So you become negative 4 times m, which is negative 4m. You become negative 4 times positive 3. Negative 3, which is positive 12. I was getting ahead of myself. And this guy is now m minus 3 times m minus 4. Now, I'm not going to FOIL that out yet because I'm hoping maybe if I do some simplifying, maybe stuff will disappear. I'm holding out that hope. By the way, that's just step 1 of the numerator. We're not even close. Now, this guy, it's the same idea. There's not much I can do. I have to multiply u by m squared over m squared. Right, I have to multiply u by m minus 3 over m minus 3. Okay, so similarly what we have is we have 16 times m, 16m, 16 times negative 3, which is negative 48. Okay, this is a minus sign. So what we're going to do is, why don't I do what I did before and attach that and make u negative m squared. I'm allowed to do that, and do negative m squared times m, which is negative m cubed, and then do negative 4 times negative m squared, which is positive 4m squared. On the bottom, I have m squared times m minus 3. Again, I'm not going to do anything quite yet because I'm still holding hope that maybe stuff will factor and stuff will disappear. I mean, it looks like the m minus 3s have possibilities, but I don't know. That might be the only thing that goes away. I need to combine like terms up here. So that 16m and negative 4m becomes 12m. Negative 64 and what was that, positive 12 is going to be negative 52. Yeah, I don't know. It doesn't look too promising. All over m minus 3, m minus 4. Okay, all over nothing. Nothing at all combined. So let's just write it out in standard form. Negative m cubed. Oh, wait a minute. This might be factoring by grouping. Oh, get out of here. This might be factoring by grouping. All right, hold on. Plus 4m squared plus 16m minus 48. No, it won't be. So close. No, there's nothing we can do. Nothing we can do about that. That's going to be all over m squared m minus 3. So now that I have a fraction over a fraction, what I do is I flip and multiply. So that gives me not much I could do out here. I can factor out a 4, but I think that's the best I could do. So 4 times 3m minus 13 all over m minus 3 m minus 4, and then since we're dividing a fraction, let's multiply its reciprocal. So we have m squared m minus 3. We can see the m minus 3s now will cross out. This is just negative m cubed plus 4m squared plus 16m minus 48. Nothing at all is going to happen with that. Since I'm multiplying fractions, I can cross out the m minus 3s. And that's going to leave me with 4 times parentheses 3m minus 13 times m squared all over, well, yeah, I'm not going to multiply it out. M minus 4 times negative m cubed plus 4m squared plus 16m minus 48. So I'm going to leave it like that. Boy, is that not pretty at all. But that is an answer. If you wanted to, you can FOIL this out on the bottom. You can maybe make that 4m squared, make it look a little bit prettier. But you know what? After all of this, I think we can be okay with that. Solve 1 over r minus 2 plus 1 over r squared minus 7r plus 10 equals 6 over r minus 2. Let's do this. Since you guys are the same exact fraction, u and u, why don't I subtract 1 over r minus 2 from both sides? I'm allowed to do that. Kind of thinking outside the box here. When I do that, you go away. I'm left with 1 over blah, blah, blah equals 5 over r minus 2. Now, why did you go blah, blah, blah is what you're asking. Well, I'm not a vampire, that's for sure. But if I look at this, I should be able to look at this and say, I could FOIL that. Yeah, I can FOIL that just fine. So you become r squared minus 7r. Bleh. If I can factor that, it won't do that. Two numbers that add up to negative 7 and multiply out to negative or positive 10 are going to be r minus 2 and r minus 5. And this so happens to be a r minus 2 already. So maybe to even things out, I can multiply the top and the bottom here by r minus 5. Yeah. And what this will do is this will give me the same exact denominator. So you stay 1. This becomes r minus 2, r minus 5. You distribute to 5r minus 25. And you are also r minus 2 over r minus 5. Now, a fun little fact is if I have 1 over a denominator equals 1 over the same denominator, just set the tops equal to each other, baby. 1 equals 5r minus 25. 1 equals 5r minus 25. Add 25. Add 25. Cross u out. 26 equals 5r. Divide by 5, divide by 5, and r will equal 26 over 5. And that's it. Solve 1 equals 1 over x squared plus 2x plus x minus 1 over x. All right. What we have is we have 1 on the left. Okay. I could factor out an x here, which gives me x plus 2, plus x minus 1 over x. Now, right now, what I have is I have 3 different looking denominators. What I can do is I can make you x plus 2 over x plus 2 to match that guy right there. Okay, I'm going to keep you that way, x plus 2. And what I'm going to do is I'm going to multiply this guy by x plus 2 over x plus 2. That way, u will now be x times x plus 2. All right? Now, this becomes a FOIL problem. Okay, x times x is x squared. Let's do this. Let's wave our hands a little bit. Plus 2x minus 1x is plus x. And then times negative 2. Now that we have 2 fractions of the same exact denominator on the left, okay, I'm just rewriting the left. Now that I have 2 fractions with the same exact denominator, I can combine like terms, which really means the 1 and the negative 2 become negative 1. So x squared plus x minus 1 equals x times x plus 2. Now, since the denominators are the same and we're equaling each other, what we can do is just say, well, let's just set this top stuff equal to each other. U equals u. Okay, so let's write that over here. Okay, that's a little rule that we're allowed to do. Now, before I do too much, why don't I distribute that? X squared plus 2x equals x squared plus x minus 1. X squared on the left and an x squared on the right are going to cancel each other out, leaving us with 2x equals x minus 1. Subtract x from both sides, cross u out. 2x minus x is just x. It looks like x equals negative 1, which we're allowed to have. No domain restriction issues whatsoever. That's not going to ruin anything. The only domain problems we'd have to worry about are 0 and negative 2. Negative 1's not part of it. So that's going to be our guy.